Okay, I want to pick up this video right where we left off the last one, and I want to begin talking about outliers. We've talked about measures of center, we've talked about measures of spread, and measures of spread allowed us to determine where things are expected, where observations are expected, and it's based on the shape of the distribution. We talked about measures of relative standing, and the last topic I covered was z-scores. And a z-score measures how many standard deviations an observation falls from the mean. And so when we talk about outliers, we're talking about the observations that fall outside where we expect them to fall, the ones that we don't expect to see. Now, the way that we set this up is based upon where we've been. We said in symmetric and skewed distributions. Remember, symmetric, let me go ahead and get a pointer here because I'm always like my pen. Symmetric distributions, we'd be using the empirical rule. Skewed distributions, we'd be using what we call the modified empirical rule. But regardless of which of those we're expecting or looking at, we're expecting observations to fall within two standard deviations. And so we're going to go and say those that fall outside two standard deviations are not expected. Those are going to be called outliers. And the only thing that changes when we move from the symmetric or the skewed distribution to when we're working with Chebyshev is we don't know the shape, so we have to hedge our bets a little bit and go outside x bar plus or minus 3s. Now I could just as easily say mu plus or minus 2 sigma, mu plus or minus 3 sigma, and you can see that I use these symbols kind of interchangeably as we go. It doesn't matter if you're talking about populations or samples, the idea stays the same. All right, we're going to say that outliers indicate one of the following problems. So if you find an outlier, one of three things has got to be true. One, the observation may be miscoded. Years ago, I used to collect survey data by taking a survey in class, and I would ask students to give me answers to various questions, and then I would take the answers they gave me home, and I would enter them by hand. Well, with a large number of students, it took a long time to enter it, so I got really fast at entering data. But by going really fast, there was also the chance that I may have messed up. And I remember one semester, I asked the age of students, and when I looked at the data set that I had entered, I had a student who was 222 years old. And I thought to myself, wow, that's an old student. I don't remember seeing any. They must have looked good because I didn't notice anybody that old. And of course, I'm joking because I miscoded. The student was really 22 years old, and I had hit the 2 a third time and entered it as 222. Now that observation showed up as being unexpected. It fell outside where we expect the student's ages to fall because it was miscoded. And you'll see this from time to time. Occasionally you have an extra 0 on your data set, or maybe a misplaced decimal point. Think about it, your GPAs, if you forgot to put the decimal point in, instead of like a 3.2, all of a sudden you have a 32 GPA. Then it's miscoded. It's an outlier because of it being miscoded. All right, second one, the observation comes from a population different than the one specified or the one that you think you're using. Occasionally with real estate data, you get a home and you look at the sales price of a home and you're like, wow, that's huge. It usually happens because the house price is really, really large. And usually, well, I shouldn't say usually, sometimes when you're doing that, it's because it doesn't really come from the area you thought. I remember once a student was working with homes over in Pinellas County, and they got a home. Most of the homes were in like the $300,000 range, $200,000 to $400,000, let's say. And one of the houses was like $3.2 million. And at first it was like, well, he just probably put an extra 0 on it, but that wasn't the case. It was $3.2 million. And then when they looked a little closer, it's because the house that they were working with actually was on the Gulf of Mexico. It was a couple of streets, maybe half a mile from the neighborhood they thought they were working in. But because it came from a half mile in a specific direction, and that direction landed you on the Gulf of Mexico, the home price was a lot higher, which you can imagine it would be. But that observation came from a population of homes different than the one the student thought they were working with. And so that could be a reason. And then thirdly, the observation is a result of what we're going to say rare chance. And I'll use this word loosely here. If you think back to the way we just defined outliers, we said outside x bar plus or minus 2s in mound-shaped distributions, outside plus or minus 3s when we're using Chebyshev. And think about those rules. The empirical rule says 95% fall within 2. The modified empirical rule says somewhere between 90 and 100% fall within 2. Chebyshev says at least 89% fall within 3 standard deviations. And so there's going to be a certain percentage of the data that falls out there, that falls further out, further than 2 or further than 3 standard deviations. And so those are the ones we're calling outliers. a rare chance. And depending on which data set you're working with, it could be as much as 10 or 11%. So I'm using the word rare, but I'm using it loosely. All right, so that's the outlier. That's defining outliers. My dog is having a little fit in the background, so I hope you stop. Her name is Rain. Hey, Rain. Rain. Shh. Sorry about that, folks. All right, so here's how I want you to think about it. There's your little outlier. Usually you don't hear dog noises in my videos. Chip example. When I do this lecture live, I bring my poker chips, and you guys probably all remember my poker chips from the first day of class. They're in that little plastic bucket, and in this bin of chips, 95% of the chips are red, and 5% are white. Okay, so I set up an empirical rule. And so I think I actually have that in your notes here. I do. 95% are red, 5% are white. And so you can think of this as being an empirical rule population. Within 2 standard deviations would be 95% of your observations. Outside of 2 standard deviations would be 5%. So I set it up. And what I try to show students, or what I try to explain to students, is that if you were to randomly pick a chip, while you could see a white one, it's possible to see a white chip, it's very likely that you're going to get a red chip. And I tell my students, and this is a true story, I tell my students that I've been doing this chip example for years and years and years and years. At last count, I was approaching 250 times, because I do it in every section, every semester, and let's face it, I'm getting old. So 250 times, the chip examples really only failed me twice. And so I'm amazingly ahead of the game in terms of what's expected. So anyway, I set this up, and then rather than pick the chip myself, which students would tend to doubt that I would do it fairly, I let them pick it. So I had to imagine, if you will, I have this bucket of chips, and I'm just kind of shaking them to mix them up, and I go to a student in the front row, and I say, all right, now please pick a chip. Just reach in without looking and pull out one chip. And I set it up in such a way, it's not going to translate on this video, I'm sure, but I set it up in such a way so everyone's expecting the red chip. And darn it all, don't you know what happens? A student reaches in, and they pull out a white chip. Now, typically what happens when that happens is the class kind of laughs. They think that's funny. There's this joint mentality of, hey, we got you. You were expecting a red one. We got a white one. Ha, ha, ha. And it's pretty funny. And I kind of laugh it off and say, well, there you go. What are you going to do about that? And so I go to my next student, and I have he or she reach in, and darn it all, don't you know, they pick out a white one too. And it's at this point in time, one of two things happens. Either students laugh louder, which happens from time to time. They're like, oh, wow, we got you twice now. Holy cow. Or students start to raise an eyebrow. And then I go to a third student, and again, a white chip is selected. And it's at this point that almost everybody in the class starts to begin suspecting that perhaps I've lied to them. And they usually don't call me a liar. They usually say something like, oh, wait a second, this is weird. What's going on? Are you sure you got the right chips? Now, what's funny for me is that occasionally after that third white chip is selected, there's a student who laughs even louder. And it's funny because every now and then, every semester, there's usually one student who I could pull out 100 white chips in a row. Just reaching in, pulling out a white chip, and they'd be laughing. They'd be like, wow, that's funny. And they would laugh louder and louder and louder and louder, and they would never really get my point. As you begin to see these white chips after white chips after white chips, at some point, we expect a red. At some point, you got to start saying, wait a second. And so we pick, let's say, I'm just going to use a W, white, 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 and on and on and on and on and on it goes. Occasionally a red chip will come out. But most often not, it's white chip after white chip after white chip. And at some point, you got to say, wait a second. Now, here's the problem we have with this. I want you to say, wait a second, right there. And while you're watching this video and you hear me talk about it, you're probably thinking, oh, I would have done it. I guarantee you wouldn't have. Nobody ever says after the first one, wow, you're lying. And that's when you need to, because a chip, in the context of this example, a chip represents a sample for us later on. We only get one sample. We get one look at the population. If it's what we expect, if you pull a red chip out, you're done with it. You just move on. If you pull a white chip, you say, hold on, I don't believe it. I don't believe the population is as specified. And that's an uncomfortable thing for students to do. it's uncomfortable for everybody. I shouldn't just limit it to students, because very rarely will you run into somebody who, when they see that contradictory chip, that contradictory information, will they challenge the population or the person that's telling them the population. Why this is important, it helps us talk about outliers now, and when I get to do it in class, it's a fun little example. But where it's really important for us is later on when we talk about test hypothesis topic. The test hypothesis topic is a pretty straightforward idea, but unfortunately we layer it with a whole lot of symbols and terminology and what I technically refer to as crap. And so I put a whole bunch of junk on top of it, and it gets tough to remember that it's a pretty easy idea. And so when we get to the test a hypothesis topic, I'll say, all right, hold on, let's take a time out. It's a little, I can tell when I look at students, I can tell when it's a little challenging or something's not right. I say, think back to when we talked about the chips. Remember, we had 95% of them were red. We reached in, we pulled out a white chip. At this point, you'd call me a liar. That's basically what we're doing. The terminology we'll use, because I know some of you guys have seen some of this before, the terminology that we'll use in test hypothesis is we won't say the population is lying or Mark is lying. We're going to say reject the null hypothesis, because a null hypothesis is going to be what specifies what's expected. And so you may remember saying things like at alpha equal 0.05, we reject H naught. If you do, that's where I'm heading. If you don't, if you're like, oh my gosh, I've never heard that before, don't worry about it. We'll get there. That's chapter, that's later in the book. I don't even know what chapter it is. But we'll get there when we do the inferential work. So anyway, that's my chip example. It's worth talking through, even though you're not going to get a chance to see it live. All right, so we talked about what an outlier is. I'll give you a little example. How do we detect it? Well, there's two methods. One should make complete sense. This one, the z-score method. Use the z-score for an observation and the shape of the distribution that it comes from. And this piece here, the shape of the distribution that it comes from, you may not even need to consider that to determine if an observation is an outlier. Okay, if you're following along everything we've done here in Chapter 2, you understand measures of center, you understand measures of spread. We have these rules that tell us what's expected, what's not expected. If it's not expected, we call it an outlier. Well, rather than looking at mu plus or minus sigma, mu plus or minus 2 sigma, mu plus or minus 3 sigma, we can just take a look at the z-scores. Because mu plus or minus sigma we saw a little while ago, that could be the z-score plus or minus 1. Then you move out to plus or minus 2, plus or minus 3. So if I tell you have a z-score of 4, that's going to be an outlier. And I'll give you some examples in just a second. So that's the z-score method. The second method is the box plot method. And this is a graph. This is a picture. And back in the day, this was a pain in the butt type of graph because you had to draw it by hand. Well, now we don't. We just have to be able to interpret them. And I'll give you some examples in a second, and we'll talk about it. When I look at examples, I'll show you how they're found as well. Graphical display that utilizes the quartiles. The quartiles do a better job of detecting outliers than the z-score, because the z-score, I'm going to draw the formula up here, involves the mean. Now, earlier we had a conversation where we talked about how the mean chases the tail or chases the outliers in the distribution. So the mean is affected by the outliers that we're trying to detect. And so we generally say the box plot method is, we don't use the word better, we say it's more sensitive. In other words, it's a better method of detecting outliers. Those borderline observations that are pretty far out there, the box plot will say, yeah, they're outliers. The z-score will say, yeah, not so much. The symbols that our software uses, these are statistics software symbols. The asterisk indicates something called a suspect outlier. I'll put in little quotes here. The O is going to indicate an outlier. Sometimes people will refer to that as a highly suspect outlier. I'm just going to use the phrase suspects and outliers. Depending what software you use, these symbols may not be the same. In fact, in some software that I've seen, they actually flip-flop. The O indicates suspects and the asterisk indicates outliers. But this is what we're going to be working with our statistics software. So let me give you a couple examples. Let's start with the z-score method. And here's how I'm going to do it. If you're working with Chebyshev and you have a z-score of 1.2, is that an outlier? Now keep in mind what that's saying. The observation falls 1.2 standard deviations from the mean. No, that's not an outlier. Chebyshev says if it's outside of 3. Okay, not an outlier. Not an outlier. It's 2.2 standard deviations below the mean. Ah, there we go. That's an outlier. Okay, 3.2 standard deviations above the mean. If I go to an empirical rule or a modified empirical rule, 1.5 below, not an outlier. 2.5, now it's an outlier. And then of course 3.5, you're going further. The plus or minus doesn't really matter when you're trying to determine outliers. It's the number that you're looking at. What you're going to notice is that if you get a value bigger than 3, it doesn't matter what distribution you're working with. You don't have to worry about the shape, because numbers 3 or more, -3 or below, those are outliers. Numbers less than 2, between 2 and -2, those are never going to be outliers. The only time you have to consider the shape is, what if you see something like a 2.2 here, or -2.2, or a 2.5, or a 2.4. Anything that's between 2 and 3, you need to pause and remember which rule you're working with. If it's the empirical or the modified empirical, those 2s, those -2s, those are outliers. If you're working with Chebyshev, they're not. So hopefully that makes sense. I think the z-score method does a good job of summarizing a lot of the ideas in the descriptive statistics topic. All right, so that's the z-score method. The box plot method, we're going to allow our software to generate a box plot. And there are the symbols again. There's an example. The television times. One semester I asked my students, how many hours a week do you watch TV? And this is a vertical. Okay, here's the number line over here. You can ask for a vertical or a horizontal box plot. And you can see that there are different symbols used. Now, just a quick lesson on how the box plot is found. This value right here, that's the lower quartile. So if you came over here, what is that about? Maybe like 5 hours a week. That's the lower quartile. This value here, which is this guy, that's the upper quartile. And so 25% of the observations are there, 75% are there. So half your data falls in the box. By the way, this is the median in here, that guy. That's the median. The difference between the quartiles, and you'll never need to use this, is called the interquartile range. If you go 1.5 of those, you get to right about here. And then you go 1.5 more, whoops, there's a nice straight line, you get to about there. This is called an inner fence, that's called an outer fence. And you can see that my symbols change based on where they're located relative to those fences. Here, what I would expect you to be able to do, see if this is challenging for you. I'd expect you to say I have 3 suspect outliers and 2 outliers. That's it. Now, I can also ask the software to break the data down a little further by the sex of the student. So here we have males and females. For the females, I have 1 suspect outlier right there. I have 1 outlier. For the males, I have, what is that? 1, 2, 3, 4 suspects and 1 outlier. So it's very easy to identify outliers when we're working with the box plots. Sometimes they're called box and whisker plots, box plots, either's fine, doesn't matter to me. And so that's how we identify outliers, both using z-scores and box plots. All right, here's what I want to end on. So I have a data set, this is from several years ago, but you can see I have certain numbers that are in red, and what I would like you to be able to do is think about how you would interpret these values. And when I ask you to interpret, make sure you interpret in the words that are prominent. I'll give you, for instance, when folks interpret the mean for me, sometimes they give me this information. The mean is 21.816. And they'll get projects back, or anything that they're giving me that says that on their back, and they'll be like, why did you take off points? And I will say, because you didn't add any information. You didn't add any value to what I see on the printout. The printout tells me the mean is 21.816. Add value to that. Tell me that the average age of the 375 students sampled was 21.816 years. Give me variables. Give me sample sizes. Give me the units of measurement. The average distance. I'm trying to think what distance represented that particular semester. It's been a while. The average distance of the 375 students was 15 whatevers miles. Maybe I asked them how many miles did they live from campus. I think that was what I asked. The average distance, someone lived 140 miles away that particular semester. That's right. So I'm sorry, this is the third quartile, my bad. So what does that mean? Third quartile, let's get that right. 75th percentile. 75% of the students live less than 15 miles from campus. 75% of the students live less than 15 miles from campus. 25% of the students live less than 1 mile from campus. The median, half the students watch less than 8 hours of TV a week. Half the students watch more than 8 hours of TV a week. The hardest one is this guy, the standard deviation, because you can't just say, the standard deviation is 0.4. What does that mean? Well, I know, and I'll tell you, the GPAs have a fairly mound-shaped distribution. Sometimes it's symmetric, sometimes it's a little skewed depending on the data that I'm looking at. And so when I know that we're working with a symmetric distribution or a skewed distribution, I know most of the observations fall within 2 standard deviations of the mean. I can do better than that. Most of the GPAs fall within 2 standard deviations of the mean. I can do better than that. Most of the GPAs fall between 2.3 and 3.9. That's how I would interpret. Most of the student GPAs, most of the 269 student GPAs fall between 2.3 and 3.9 GPAs, what are grade points, whatever they're called. That's how I want you to interpret descriptive information. Tell me what the numbers mean in the context of the problem. All right, that's a good place to stop. That summarizes pretty much all the descriptive statistics stuff we've done. Hopefully that's not too much for you, and I'll see you soon.